Okay guys, so back here for number 3 from 2018 non-calculated problem. So it says the graph of the continuous function g, so this function is continuous, and it's the derivative of f, so we could also call this f prime, which means f prime is differentiable since, f's differentiable since f prime exists everywhere. Function g is piecewise linear function, and then this section here is that function right there. Okay, so it says if f of 1 equals 3, what is the value of f of negative 5? So we're going to take 3 plus the integral. We can only start at 1, so we'll go from 1 to negative 5 of g of x. Except I don't like that, so I'm going to flip this around so I can look at it, but I got to change this sign to negative, so we'll go from negative 5 to 1 of g of x. And if I go look here, this area is 9, that's 1.5, so that'll be 10.5. No area there, and then this little area right here would be 1, so that would be count negative, so we'd have negative 10.5. Plus 1 would be negative 9.5, but we've got a negative sign in front of it, so we'll add that. So we'll go plus 9.5, so get 12.5 or 25 halves. Okay. Part B says evaluate the integral from 1 to 6. So if I'm going to do from 1 to 6 of g of x, I'm going to have to split it into pieces. So I'm going to go from 1 to 3, and then from 3 to 6. It's their different pieces here. And from 3 to 6 is going to be that function 2x minus 4 squared dx. So this part I'm just going to look. So from 1 to 3, that's just an area of 4. And this one, I can do this function, or I could square this out, whichever one makes you feel more comfortable. And then distribute that 2 through there, if you want to do that. I'm okay doing this because I'm going to start with an x minus 4 to the third. I'm going to think, well, if I took this derivative, I'd have a 3 out there, and I don't want a 3, so I'm going to make a 3 go away, and I'm going to make a 2 appear. And I'm going to evaluate this from 3 to 6. So I got a 2/3, I'm going to go ahead and factor that out. If I plug a 6 in, I get 2 to the third. And if I plug a 3 in, I get negative 1 to the third. So I still have this 4 here. So I get 2/3, 8, and then I get plus 1 is 9. 3 goes to 9, 3, 6, so that's a total of 10. That's that there. And it says, at what open intervals, if any, is the graph both increasing and concave up? Give a reason for your answer. So we're going to, write out that cheat sheet. F prime positive means F increasing, blah, blah, blah. So if increasing is code for, so if F is increasing, that means that F prime is positive. This is a picture of F prime. And then if F is concave up, that means F double prime is positive, which is the slope here. So I'm looking for places where this has a positive value and a positive slope. That would be from 0 to 1 and from 4 to 6. And my reason for that would be these are all the places where F prime is both positive and increasing. So, or where F prime and F double prime are both positive, your choice on the wording. And then we're to D. So it says find the x-coordinate of each point of inflection. So a point of inflection is a place where the second derivative changes signs. So you'll notice here it goes from 0 to positive, that's not a sign change. Positive to 0, not a sign change. 0 to positive, nope. Positive 0, nope. 0 to negative, nope. But right there, the second derivative changes signs. So I would say at x equals 4 is my point of inflection because that's the place where f double prime or g prime changes signs. Okay, guys.